The floor beneath everything you have ever touched is not the bottom. The ground feels solid. The table holds its shape. The chair takes your weight. And every instinct you own insists that the physical world is a finished, permanent thing that was here before you and will be here after. But there is a quiet result buried in modern physics that says otherwise. And once you understand it, you cannot unsee it. The stability you trust is not proven stability. It is stability that has simply not failed yet. Those are not the same thing, and the gap between them is wide enough to swallow the universe. For most of history, the question of why anything exists at all, and why it holds together rather than coming apart, belonged to dreamers and thinkers who had no instruments to test it. Physics stayed away from it. The way you keep your distance from a door when you are not sure you want to know what stands behind it. That distance is gone now. In the last couple of decades, and faster in the last few years, careful measurements have started pressing directly against the deepest layer of all. And what they are revealing is not comforting. If questions like this keep you up at night the way they do us, take a second to like the video and subscribe. It would honestly mean a lot to us. To see why physicists grew uneasy, you have to start with a single number, pulled out of the largest machine human beings have ever assembled. Deep underground, in a ring of superconducting magnets stretching for miles, beams of particles were driven to nearly the speed of light and smashed together trillions of times, all to catch a glimpse of one fleeting thing that had been predicted for half a century, but never seen. The thing was the field that gives matter its mass, the invisible medium that drags on particles and lends them weight. And the particle that signals its presence finally flickered into the data. Its mass came out to roughly 125 times the mass scale physicists use for such things. And at first that looked like nothing more than a triumphant data point, a box to be checked. A decades-long hunt finally closed. It was not nothing. In the years that followed, several independent groups took that mass and fed it into the equations that govern the field filling all of space. The field that quietly sets the rules for every particle and every force. And the answer that came back was the kind of answer that makes careful people go very quiet. At that particular mass, the vacuum of space, the empty stage on which all of physics is performed, does not sit at the lowest point it could occupy. It sits in a shallow dip a little above the true bottom, a resting place that feels final but is not. The technical word for this condition is metastable, and the word carries a warning inside it. Metastable does not mean safe. It means safe for now, under present conditions, as long as nothing comes along to push it over the edge. Picture a marble resting in a small hollow, scooped into the side of a hill. From where the marble sits, the world looks level. It has been there a very long time. Nothing has nudged it. You could glance at it and decide it will stay forever. But the hollow is not the foot of the hill. There is a deeper valley below, separated from the marble only by a low rim. And the only reason the marble has not rolled down into it is that nothing has yet given it the small shove it would take to clear the rim. The vacuum of space, the substrate underneath every atom and every ray of light, may be that marble. The equations suggest it is not lying at the true floor of reality. It is balanced in a higher dip, held there not by permanence, but by patience, by the simple fact that the shove has not arrived. So what would it mean for the shove to arrive? This is where the mathematics turns from abstract into genuinely chilling, and it was worked out in detail more than 40 years ago by physicists studying exactly this kind of unstable emptiness. They described a process in which, at any point in space and any moment in time, the ordinary churning of quantum uncertainty could nudge a tiny patch of the false floor over the rim and let it drop into the true floor below. The instant that happens, that patch becomes a seed. A bubble forms. Not a bubble of gas, not an explosion, but a region where the deeper, truer vacuum has taken hold. And it begins to grow, swelling outward in every direction. Think of water cooled carefully below its freezing point, while staying perfectly liquid, held in that strange suspended state, only because nothing has given the ice anywhere to begin. Drop in a single speck of dust, tap the glass once, and the whole volume seizes into ice in a heartbeat. The change does not creep across the water. It takes it all at once, because the liquid was never truly stable. It was only waiting. The bubble of true vacuum behaves the same way, except the container is not a glass. It is everything. And on the inside of that bubble, the constants of nature are reset. The mass of the electron, the strength of the forces that bind particles into atoms, the very rules that let chemistry happen, all of them shift to new values. Under those new values, atoms as we know them cannot hold together. Matter, as we understand it, cannot exist. Whatever survives on the far side of that wall, it is not the world we live in. And here is the detail that turns a frightening idea into something almost unbearable to think about. The wall of that bubble expands at the speed of light. Light is the fastest messenger the universe permits. Nothing, no signal, no warning, no shadow of approaching change can outrun it. So the wall and the news of the wall travel at exactly the same speed. The light reflecting off that advancing boundary arrives at your eyes at the same instant the boundary itself does. There is no early glimpse, no flash on the horizon, no rising hum. The event and the announcement of the event are the same moment. You would not see it coming, because seeing it coming is forbidden by the very structure of space and time. Physics, in this case, does not offer a way to detect the danger. It offers only a description of how the disappearance would work. Silent, total, and impossible to anticipate from the inside. Now, it would be easy to spiral into dread here. So it is worth being honest about the timescales. If our vacuum truly is metastable, the most careful estimates put the expected wait for such a bubble to form spontaneously near our corner of space at numbers so vast they dwarf the current age of the universe many times over. The point of all this is not that the sky is about to crack open tonight. The point is far stranger, and in a way more profound. The point is that the permanence we assign to physical reality is not a property the universe has promised us. The solidity is provisional. The ground is not resting on bedrock. It is holding a position. And the fact that physics can even raise this possibility in equations rather than in fearful imagination tells you something has shifted. The deepest layer of reality is not the unshakable foundation we always assumed. It may be a temporary arrangement, and the equations cannot fully explain what is keeping it in place. That uncertainty about the foundation is not an isolated worry. It connects to what may be the single most embarrassing unsolved problem in all of science, a discrepancy so enormous that physicists have learned to talk around it rather than face it directly. The problem concerns the energy of empty space itself. According to the same quantum theory that has been tested more precisely than any idea in the history of human thought, accurate to more decimal places than any other framework we possess, empty space should not be empty of energy. The constant fizz of particles flickering in and out of existence should give the vacuum a baseline energy. And that theory predicts how much. The number it predicts is staggeringly large. Then astronomers went and measured the actual energy of empty space. By watching how the expansion of the universe behaves, by tracking the motion of distant galaxies, by reading the geometry of the cosmos on its grandest scales, They got a number too. And the measured number is smaller than the predicted number by a factor so absurd that ordinary language has no grip on it. A 1 followed by roughly 120 zeros. To feel the size of that gap, consider that the total count of atoms in the entire observable universe is a 1 followed by around 80 zeros. The mismatch between what the theory demands and what the cosmos actually contains is vastly larger than the number of atoms in everything we can see. It is not a small error waiting for a tidy correction. It is the largest disagreement between prediction and observation in the history of science, and it has sat in the equations, unresolved, for decades. Try to picture an engineer who calculates that a bridge should weigh as much as a mountain range, then weighs the actual bridge and finds it lighter than a feather. And the bridge is standing, carrying traffic, perfectly fine. That is the situation physics is in with the energy of empty space. The calculation and the reality are so far apart that the simple fact that the universe holds together, that galaxies formed at all, that space did not tear itself to shreds before the first star ignited, becomes something that demands an explanation we do not have. By the most straightforward reading of the theory, reality should have ripped apart at the very beginning. It did not. Something is keeping the books balanced to a precision that looks impossible, and no one can say what. Ask yourself plainly, if the math is wrong by that much and we are still here, then what exactly is holding everything up? That question has no accepted answer, and the deeper you push toward the foundations, the more such questions you find waiting. It would be one thing if this energy of emptiness were a mere accounting trick, a number that lived only on paper. It is not. The emptiness is physically real, and it pushes on things. Bring two perfectly smooth plates extraordinarily close together in a vacuum, closer than the width of a hair, and they feel a faint attraction drawing them toward each other, not from any charge, not from gravity, but from the restless quantum activity of the supposedly empty space around them. The constant flicker of particles winking in and out has slightly less room to churn in the narrow gap between the plates than in the open space outside, and that imbalance produces a measurable force. This has been demonstrated in laboratories. Empty space presses on matter. The nothing that surrounds you is doing something, all the time, and it does it whether or not anyone is measuring. The vacuum is not the absence of everything. It is a seething, structured medium that merely registers, to our coarse senses, as nothing at all. And there is a reason the present arrangement of that medium should make you think back to the marble balanced in its hollow. Because the universe appears to have changed its footing before. In its first searing instant, when everything was vastly hotter and denser, the rules were not the same as they are now. The field that gives matter its mass had not yet settled into the value it holds today. The forces we now experience as distinct were blended together in a single hotter behavior. As the cosmos expanded and cooled, it passed through transitions, moments when the underlying fields dropped into new resting states, like steam condensing into water and then freezing into ice, each step locking in properties that had been fluid before. The constants we now treat as eternal were, in this picture, frozen into place as the young universe cooled, the way a pattern of cracks is frozen into a sheet of ice the moment it sets. Which means the stability we live inside is not an original, necessary feature of existence. It is a residue, the settled outcome of ancient transitions, a configuration the universe fell into rather than one it was obliged to have. And if the universe found its current footing by cooling into one resting state out of others that were possible, the unsettling question writes itself: is the state we are in the final one, or merely the latest? And the strangeness of the cosmos is not limited to the rules it follows, or the energy of its emptiness. It extends to the simple matter of what the universe is made of. Because by every honest measurement, the things we can see and name make up only a small sliver of what is actually out there. When astronomers weigh galaxies by watching how fast their stars wheel around the center, they find far more pull than the visible matter can account for. The stars at the outer edges move so quickly they should fly off into the dark. And yet they hold their orbits, gripped by the gravity of something that gives off no light, absorbs no light, and casts no shadow. Something we detect only by the way it tugs. This unseen substance appears to outweigh everything luminous by a wide margin, an invisible scaffolding threaded through every galaxy, holding the bright structures together. And beyond even that, the accelerating stretch of space points to a second hidden presence, the energy of the vacuum itself, which by most accounting makes up the largest share of everything there is. Added up, and the ordinary matter that forms stars and planets and bodies, the only kind we have ever touched, the only kind our instruments were built to see, turns out to be a thin froth, riding atop an ocean of two things we cannot identify. We have spent our whole history studying the visible crumbs and calling it the universe, when the bulk of reality is composed of substances that have no names, because we do not yet know what they are. The cosmos is not merely strange in its rules. It is overwhelmingly made of the unknown. There is a class of numbers woven into the structure of the universe that deepens this unease in a different way. These are not numbers anyone chose, and they are not numbers any deeper theory has so far been able to derive. They are simply the settings the world arrived with, and the strange thing about them is how narrow the range of workable values turns out to be. Nudge several of them even slightly, and you do not get a different kind of universe. You get no universe capable of structure at all, no stars, no chemistry, nothing that could persist long enough to be called a thing. Start with the force that shapes the cosmos on its largest scales. Gravity is, oddly, the weakest of the fundamental forces by an almost laughable margin. It is so feeble at the scale of individual particles that it barely registers, and it only becomes the dominant force in the room once you gather matter into masses the size of moons and planets and stars. And yet this whisper of a force is what pulls gas into the burning cores where the elements are forged. What gathers those elements into worlds? What assembles stars into galaxies, and galaxies into the vast luminous web that fills the sky? Now imagine adjusting the strength of that force by an amount so tiny it has no analogy in everyday life. A fraction with dozens of zeros after the decimal point. Strengthen it by that sliver, and the early universe would have pulled itself together too violently, collapsing in its first moments, before stars ever had a chance to form, before fusion could begin, before the carbon and oxygen that make complexity possible could be cooked into being. Weaken it by the same sliver, and matter would have flown apart too freely, never gathering into stars at all, leaving behind a thin, cold, expanding haze that never lit a single fire. Imagine a dial that runs across an unthinkable range of possible settings, and a target zone narrower than anything you could mark with the finest instrument ever built. Land outside that zone, anywhere outside it, and the story ends before it begins. The dial that controls gravity landed inside the zone. Physics can tell you that it did. Physics cannot yet tell you why the zone exists, or why the setting fell where it did. And gravity is only one dial among several, each one tuned with the same uncanny exactness, each one raising the same question and leaving it unanswered. One of the most beautiful examples of this came not from a measurement at all, but from a piece of reasoning so daring it still has few equals in the history of science. In the middle of the last century, An astrophysicist studying how stars manufacture the elements realized there was a problem with carbon. Carbon is the spine of all known chemistry, the kind of intricate, self-assembling molecules that make complexity possible, simply cannot be built without it. But he also understood how carbon is made. Deep in the heart of a star, 3 helium nuclei must collide and fuse, almost simultaneously, to produce a single nucleus of carbon. The trouble is that such a triple collision is extraordinarily unlikely to leave anything stable behind, unless the energies involved happen to line up with a special internal state of the carbon nucleus, a kind of resonance, a matching note that lets the reaction ring true and proceed efficiently. So he reasoned backward from his own existence. Carbon-based chemistry was clearly abundant in the universe. He was, after all, made of it. Therefore, the carbon nucleus must possess a resonance at a very particular energy, one that no one had yet found. Because without it, the universe would contain almost no carbon, and none of the chemistry that depends on it. He calculated where that resonance would have to sit, walked into a laboratory, and told the experimenters precisely what to look for. They looked. It was there, almost exactly where he had said it would be. He had used the bare fact of his own presence as a measuring instrument, and the universe confirmed the reading. And the tuning runs deeper than that single note. The resonance that lets carbon form sits at one energy. The corresponding resonance in oxygen, the next element up the chain, sits just low enough that carbon is not instantly devoured and converted into oxygen as soon as it appears. Shift the carbon resonance down by a few %, and carbon would scarcely form. Shift the oxygen resonance up by a hair, and nearly all the carbon would be transformed away before it could ever escape into space to become part of planets and rivers and living things. Both values are positioned, and positioned together, in the narrow band that permits the rich chemistry the universe actually contains. Here again, the standard framework offers no derivation. The numbers are simply what they are, sitting exactly where they need to sit, and the question of why hangs in the air with no scientific answer beneath it. There is a third dial, perhaps the strangest of all, and it returns us to the energy of empty space. A famous figure in the history of physics once inserted a term into his great equations of gravity, a term representing a kind of pressure built into space itself, only to remove it later and call it the greatest blunder of his career. Once it became clear the universe was expanding, rather than sitting still. But near the end of the last century, that term came roaring back. 2 independent teams of astronomers, measuring the brightness of distant exploding stars to clock how fast the cosmos was expanding, found something their instruments should not have been able to show. The expansion is not slowing down under the pull of all that gravity. It is speeding up. Something woven into the emptiness is pushing space apart, harder and harder, and describing it required exactly that long-abandoned term, the energy of the vacuum, the very quantity at the heart of the great unsolved discrepancy. Set aside, for a moment, the impossible mismatch between the predicted and measured value, and look instead at what happens if you simply vary the measured value itself. Make that vacuum pressure a few times stronger than it is, and its outward push would have overwhelmed gravity in the young universe before matter had any chance to gather into galaxies. Space would have stretched too fast, scattering everything into a thin, structureless cold. Make it negative instead, an inward pull rather than an outward push, and the universe would have folded back in on itself within its first billion years, collapsing before the first generation of stars had finished living. Picture a rope stretched taut across a deep canyon, one rope width wide. Stray to one side and you meet one kind of catastrophe. Stray to the other, and you meet a different one. The vacuum energy has been walking that rope, without a single misstep, for nearly 14 billion years. Physics can describe the rope. It cannot tell you how the walk was found, or why the rope hangs where it does. And these are only the dials that draw the most attention. Look closer at the machinery of matter itself, and you find the same uncanny balance, hiding in places you would never think to check. Consider the force that binds the cores of atoms together. The strongest of all the forces, but one that reaches only across the tiniest distances. Strengthen it even modestly, and the simplest atom, a lone proton, would no longer be content to sit alone. Pairs of protons would lock together throughout the early universe, and the slow, steady burning that let stars shine for billions of years would never have settled into its patient rhythm. Weaken that same force, and the heavier nuclei that make up everything interesting would never hold together at all, leaving a universe of nothing but the lightest, simplest stuff. Or consider a fact so quiet it sounds like trivia. The neutron is very slightly heavier than the proton. By a hair, by a fraction of a percent. Flip that tiny imbalance the other way. Make the proton the heavier of the two, and the protons that form the hearts of atoms would themselves be unstable, decaying away, and the kind of matter that builds worlds and bodies could not endure. The difference between a universe that can hold together and one that cannot comes down, in part, to a sliver of mass smaller than almost anything else in physics. Everywhere you look beneath the surface, the same pattern repeats, values that did not have to be what they are, sitting precisely where they must sit for anything lasting to exist, with no deeper rule, yet found to require them. So we have, at the very least, a handful of settings. The strength of gravity, the resonances inside the atomic nuclei that build the elements, the energy hidden in empty space, and each one rests at a value that allows structure, complexity, and time to exist. And not one of them falls out naturally from any deeper principle we currently know. A reasonable response is to assume that this is merely a gap in our understanding, that some grander theory waiting to be discovered will one day make these numbers inevitable. Derive them cleanly the way the orbits of planets fall out of a single law of gravity, and dissolve the mystery into obviousness. That hope drove an enormous amount of work for a long time. To understand why so many physicists have quietly let go of it, you have to follow them into the strangest landscape theoretical physics has ever drawn. For a long time, one ambitious framework looked like the best candidate to finally make sense of the constants. It replaced the idea of particles as tiny points with the idea of particles as minuscule vibrating threads, and it demanded extra dimensions of space folded up far too small to ever see. The hope was that the way those hidden dimensions were curled and knotted would dictate the values of everything, that the constants would emerge as the only possibility once the geometry was understood. Then someone sat down and counted how many distinct ways those hidden dimensions could be arranged, each arrangement producing its own complete set of physical constants, its own version of physics, its own kind of universe. The count was not large in any familiar sense. It was a 1 followed by something like 500 zeros. That number is not big the way a billion is big. It is big in a way that breaks the meaning of the word. Recall that the atoms in the entire observable universe number around a 1 with 80 zeros after it. A 1 with 500 zeros is larger than that by an amount that itself defies description. And what it means is brutal for the original hope. The framework does not single out our universe as the necessary one. It offers a catalog of possibilities so immense that the word catalog collapses under it. A sea of conceivable universes, with the vacuum energy 1,000 times larger here, 1,000,000 times smaller there, and every imaginable value scattered somewhere among the rest. To say that one entry in that endless catalog has the constants we observe is not to explain those constants. It is to surrender the hope of explaining them, by making every possible answer equally available, and none of them required. A theory that quietly permits every outcome, predicts nothing in particular about the one we actually inhabit. That realization pushed some thinkers toward an even bolder idea. Perhaps those countless possibilities are not just abstract entries on a list. Perhaps they are all, in some sense, real. The seed of this notion comes from a widely held picture of the universe's first instant, in which space underwent a burst of expansion so violent and so fast that a region smaller than a single particle was stretched larger than a galaxy, in a sliver of time too short to name. That sudden swelling smoothed the early universe and explains a great deal about what we see. But follow the idea to its logical end, as some did, and you find that the swelling need not stop everywhere at once. In some regions it ends, settling into calm space like ours. In others, it keeps racing on, spinning off new regions, each one cooling into its own pocket of reality, with its own role of the constants. The expansion, in this picture, never fully stops. It keeps budding off new domains forever, an endless froth of separate universes, most of them barren, a rare few landing in the narrow band where stars and chemistry are possible. It is a dizzying vision, and it sounds at first like a resolution. If every setting of the dials exists somewhere, then of course we find ourselves in one of the rare domains where the dials permit complexity. We could hardly find ourselves anywhere else. This line of reasoning, that the conditions we observe must be compatible with our being here to observe them, is logically airtight as far as it goes. Picture someone who walks away unharmed from a volley of shots fired at close range, and marvels at the odds. The very fact that they are alive to wonder already guarantees that, by whatever route, the shots missed. The observation is correct. But notice how little it actually settles. It does not tell you why a froth of universes exists rather than nothing at all. It does not tell you why the deeper laws that allow such budding to happen are in force. It does not explain why there is mathematics for any of this to obey, why there are fields to fluctuate, why there is a stage at all. A picture that accounts for the constants by proposing that everything exists has not closed the question. It has pushed it down one level, into darkness, and the level below is harder to reach than the one we left. And the idea cannot, at present, be tested or disproven, which leaves it hovering in an uncomfortable place, perhaps profound, perhaps unfalsifiable, perhaps both at once. Step back from the cosmic scale, and you find that the strangeness is not confined to the largest questions. It is sitting inside the most ordinary motion. Every physical process you have ever watched obeys a rule so reliable it has no known exceptions, operating at every scale from the subatomic to the cosmic. For as long as anyone has been able to measure anything, and no one can say why the rule is the rule. When a system travels from one state to another, it does not wander or take a random route. Out of all the infinitely many paths it could follow, it takes the one that makes a certain mathematical quantity, computed from the energy and shape of the journey, as small as it can be. The system behaves as though it has surveyed every possible path, weighed each one, and chosen the most economical. Even though a particle setting out has no way of knowing the routes it did not take, and yet the route it takes is always the optimal one. Think of a traveler crossing unfamiliar country, who without a map and without deliberation always happens to walk the single most efficient line between where they are and where they are going. Not a line they chose, but a line written into the very shape of the ground beneath them. Every process in the universe behaves like that traveler, from the slow wheel of a galaxy to the fleeting decay of a single particle, all of them threading the optimal path without intention and without awareness. A later reformulation in quantum theory made this stranger rather than simpler. In that account, a particle does not follow one path at all. It explores every possible path at once, and the route we observe is simply the one where all the nearby possibilities reinforce one another, while the rest cancel out. The economical path is not imposed from outside. It emerges from the fact that the universe, at its base, tries everything, and only one outcome survives the interference. That is a beautiful answer, and it relocates the mystery without removing it. Why should the underlying possibilities combine in exactly the way that produces this flawless economy at every scale? The rule has been written precisely in the equations for centuries, exact and dependable, and entirely unexplained. The universe is not merely following equations. It is following the most efficient equations, behaving from the outside like something performing a vast, ceaseless computation, which forces a question few are comfortable putting into words. If it resembles a computation, what is it running on, and where did the rules come from? To chase that question, you have to go downward, into the smallest scale physics can presently describe, and ask what space itself is made of. Every instinct tells you that space is smooth and continuous, that between any 2 points, however close, there is always another point, that you could zoom in forever and find more space, endlessly divisible, a seamless backdrop with no smallest grain. That instinct is almost certainly wrong, and the mathematics that says so has been sitting in the literature for decades. One serious line of work argues that space is not smooth at all, but quantized, that it has a smallest possible size, a grain below which the very idea of distance stops meaning anything. That smallest length is fantastically tiny. A single proton is already almost unimaginably small, and this fundamental grain is smaller than a proton by 20 orders of magnitude. If you blew up an atom until it was as large as the entire observable universe, that smallest grain of space would still only be about the size of an ordinary tree. Think of a photograph that looks perfectly smooth from across the room. Lean close enough and the seamless image breaks into individual dots, each one simply on or off, with no detail hiding below the size of a single dot. The picture only appeared continuous because the dots were far too small for your eye to separate. In this view, space has dots too, set at that fundamental grain, and the smoothness you move through every day is a low-resolution illusion produced by the fact that everything you have ever touched is monstrously larger than the grain itself. Go all the way down to that scale, and space is not a fabric. It is a network, a web of nodes joined by links, where each node carries a quantum of volume and each link a quantum of area. And the geometry we experience emerges from the pattern of connections, the way the warmth of a room emerges from the unfelt jostling of countless molecules. Temperature feels like a smooth, continuous thing, but underneath it is nothing but discrete collisions. Space may feel smooth in the same way, while being, at bottom, discrete relationship. And here the ground gives way again. That network is not floating inside some deeper space. It is not embedded in anything. The network does not sit in space. The network is space, and there is nothing beneath it for it to rest upon. Which means that if you keep descending toward the foundation of the physical world, you do not arrive at some final, solid stuff. You arrive at connections between abstractions, at relationships with no underlying things that the relationships are between. The bottom of reality, on this view, is not a substance. It is a pattern of links, holding the shape of everything, made of nothing you could ever pick up. If that were the only crack in the foundation, it would be unsettling enough. But there is a deeper fracture, one that has divided physics for a century with no sign of healing. We possess two supremely successful descriptions of the world, and both are correct, and they cannot both be correct in the same place at the same time. One of them describes gravity and the grand architecture of the cosmos, the curving of space and time around mass, the bending of starlight, the slow expansion of everything, the dark hearts where light cannot escape. Its predictions have been confirmed again and again, down to exquisite precision, by clocks on satellites, by ripples in space, caught by detectors sensitive to a fraction of the width of a proton, by the silhouette of a region of no return, imaged directly. It paints reality as a smooth, continuous, gently curving geometry. The other description governs the realm of the very small, the particles and the forces that bind them, the probabilistic flicker of the quantum world. Its predictions have been verified to more decimal places than any theory in any field, ever. It paints reality as discrete, grainy, and irreducibly uncertain, a place of probabilities rather than certainties. Each description is a masterpiece. Each works flawlessly in its own domain. And when you try to force them together, when you try to write a single equation that describes gravity in the language of the quantum, the mathematics does not merely get difficult. It detonates. The equations spit out infinities, not large numbers, but genuine, meaningless infinities. Quantities that climb without limit and refuse to correspond to anything real. The machinery simply stops working. Imagine two maps of the same country, each one perfect. One charts everything west of a great river with flawless accuracy. The other charts everything east of it just as perfectly. But neither map includes the river itself, and the river is exactly where the most important things happen. The dark hearts where stars collapse are the river. The first instant of the universe is the river. The smallest grain of space is the river. Physics holds two perfect maps and a blank seam running between them, and that blank seam falls precisely across the questions of where everything came from and what lies at the bottom. As things stand, no one has stitched the maps together. No accepted theory tells us what happens inside the collapsed remnant of a star, where both descriptions must apply at once. No accepted theory describes the universe's first moment, where both are needed and both fall apart. The gap is not a small, unexplored corner. It sits at the origin and the foundation of everything, and it may not be a temporary gap at all. It may be built into the situation. There is a reason to suspect the incompleteness might be permanent, and it comes from an unexpected direction, not from physics at all, but from a result in pure logic established nearly a century ago. A young mathematician proved something that the field had assumed was impossible. And once proven, it could never be undone. He showed that any system of reasoning powerful enough to capture even basic arithmetic must contain statements that are true, but that the system itself can never prove from within. Not statements that are merely hard to prove. Statements that are genuinely, verifiably true, and yet forever beyond the reach of the system that contains them. The incompleteness is not a flaw to be patched. It is a structural feature of any sufficiently rich system of formal reasoning, guaranteed by logic itself. The reason this should haunt physics is that a physical theory is exactly such a system, a set of starting assumptions, a set of rules for drawing conclusions, and a body of predictions about what we will observe. Any complete description of reality, any so-called theory of everything, would itself be one of these formal systems. And the theorem applies. Picture a vast library that holds every book ever written, including books about the library. A collection that seems to contain everything. The proof shows that any library rich enough to describe itself must hold truths about itself that it cannot verify from inside. Truths that could only be confirmed from some vantage point outside the library. A vantage point that, if the library truly is everything, does not exist. Turn that on the universe. If reality runs on rules deep enough to generate the staggering complexity we see, then there are true facts about reality that cannot be derived from any theory built inside that reality. Not because we are not clever enough, and not because our instruments are too crude, but because of the logical relationship between a system and its own description. A complete account of everything, discovered from within everything, may be impossible in principle. Not a gap we have yet to cross, but the shape of the space we are standing in, a place where the view from inside can never take in the whole, because there is no outside to step into. If the foundations are uncertain, and the maps refuse to meet, you might hope that at least the everyday machinery of the quantum world is well understood. It is not. The most precisely tested theory in the history of science cannot tell you what it is actually describing. At its heart sits a mathematical object that captures all the possible states a system could be in, each with its own likelihood, blended together in what is called a superposition. A particle not here or there, but somehow weighted across both. A coin not heads or tails, but a smooth combination of the two, evolving smoothly and predictably according to a single elegant equation. The equation never falters and never picks a winner. It carries the blend forward in time, spreading and combining the possibilities, and it never, on its own, collapses that blend into a single definite outcome. And yet, every time we look, we find a single definite outcome, one position, one result, one face of the coin. The blend that the equation insists on is never what we see. We see a particular answer. Every time. So what happens between the smooth blending described by the mathematics and the single sharp fact delivered to our instruments? No one knows. There is no agreed-upon physical process that turns the many into the one. For 100 years, the working response has been to simply declare that the act of measurement causes the blend to resolve, without ever specifying what counts as a measurement, where the line falls between the quantum system and the device watching it, or what physically happens in that instant. It is less an explanation than a polite refusal to look, adopted because it lets the predictions march on correctly, while the deeper puzzle is set aside. And those predictions are not merely correct. They are correct to a degree that beggars belief. There is a particular property of the electron, a measure of how it responds to a magnetic field, that the theory predicts and that experiment measures, and the two agree to something like a dozen decimal places. To grasp what that means, imagine measuring the distance across a continent and getting it right to within the width of a single human hair. That is the level of agreement between this theory and the world. No other description of nature, in any field, comes anywhere close. The framework is, by an enormous margin, the most accurate set of ideas the human species has ever produced. And this is exactly what makes its silence so disorienting. We are not dealing with a vague or shaky theory that we can excuse for not knowing what it describes. We are dealing with the single most precisely confirmed picture of reality ever assembled, a picture that predicts the behavior of matter with almost supernatural exactness. And it cannot tell us what is happening in the moment we look, what becomes of the blur of possibilities, or why the world we observe is sharp and singular when the mathematics insists it should be a smear of everything at once. We have built an oracle that is never wrong about what we will see, and never able to say what is there when we are not seeing it. The closer the agreement between the numbers, the louder the silence underneath them. The strangeness becomes impossible to ignore in an experiment that has been performed countless times and never once explained away. Particles are fired, one at a time, at a barrier with two narrow openings, and caught on a screen behind it. When nothing watches which opening each particle goes through, the screen slowly builds up a striped pattern of bright and dark bands, the unmistakable signature of something passing through both openings at once and interfering with itself. A single particle behaving like a spread-out wave exploring both routes together, but place a detector at the openings. Set up anything that records which path each particle actually took, and the stripes vanish. The particles begin behaving like ordinary little pellets, each going through one opening, the pattern of a wave gone entirely. The mere availability of information about the path changes how reality arranges itself. Modern versions of this experiment can extract that path information while disturbing the particle by the smallest amount the laws of physics permit. And still the pattern collapses the instant the information exists anywhere it could in principle be read. It is not the rough physical poke of the measurement that matters. It is whether the universe holds a recoverable record of which way the particle went. Where such a record exists, the wave-like interference disappears. Where no record exists, it returns. Reality seems to respond not just to physical nudging, but to the informational structure of the situation, behaving one way when its history is, in principle, knowable, and another way when it is not. And then the experiment was pushed into territory that should not be possible. A version was designed in which the decision about whether to record the particle's path is made only after the particle has already passed through the barrier, after it has, by any ordinary reckoning, already either gone through one opening or explored both. The choice to extract or discard the path information is delayed until that part of the journey is supposedly finished. When the experimenters choose, belatedly, to capture the path information, the interference pattern is absent, as though the particle had gone through a single opening. When they choose, just as belatedly, to discard it, the interference returns, as though the particle had gone through both. The behavior at the barrier, an event already in the past, appears to depend on a decision made afterward. The history does not seem to be fixed until someone elects to read it. The past, in this narrow and carefully controlled sense, is not a finished record that the present merely consults. It is a structure the present helps to settle. Faced with results like these, physicists have split into camps, each with its own account of what is really going on. And the unsettling truth is that all of them fit every experiment ever performed equally well. One camp keeps the smooth equation and refuses to ever collapse the blend, proposing instead that every possible outcome genuinely happens, the world dividing at each quantum juncture into branches that all carry on, each containing observers convinced their single result is the only one. A river forking endlessly, every channel real, every channel carrying water onward. Another camp adds hidden machinery beneath the equation to restore a single definite reality moving along tracks we cannot see. Another relocates the whole puzzle into the expectations of whoever is doing the observing, treating the mathematical object not as a description of the world out there, but as a kind of carefully reasoned forecast, a bookkeeping of one observer's beliefs about what they are about to encounter, so that the resolution of the blend is something that happens to the observer's information, rather than to the particle. Another insists that properties are never absolute at all, that a particle has a definite position only relative to the specific system interacting with it, and no position whatsoever considered in isolation. the way a price exists only between a buyer and a seller, and not as an intrinsic feature of an object alone. These pictures of reality could not be more different from one another. In one, countless parallel worlds butt off ceaselessly. In another, there is a single hidden track. In another, the very notion of an observer-independent world quietly dissolves. And no experiment yet devised can tell them apart, because each one reproduces every measurement we have ever made. The framework that underlies modern technology, that predicts the behavior of matter to a precision beyond any other human achievement, does not come with an agreed-upon answer to the simple question of what is happening when we look. We can use it with total confidence and complete ignorance at the same time. We have built a flawless instrument, and we do not know what it is showing us. Now let the partial answer some offer to all this be examined, because it is often mistaken for a solution, when it is really a beautiful way of hiding the problem. When a quantum system in its blended state touches the wider world, collides with stray particles, scatters a few photons, brushes against the uncountable jostling of its surroundings, the blend does not vanish. It spreads. The delicate overlap between possibilities leaks outward, entangling with one particle of the environment, then another, then billions, until the interference between the branches is smeared across so much of the world that no practical measurement could ever recover it. Drop a tablet of dye into the ocean, and the color does not cease to exist. It disperses so thoroughly that no sample you could ever draw would reveal it. The dye is still there. You simply cannot find it again. This dispersal explains, with real mathematical precision, why the everyday world looks solid and singular, rather than blurred across possibilities. But notice what it does and does not do. It explains why the blend becomes invisible. It does not explain why you experience this outcome rather than that one. It does not turn the many into the one. It only scatters the many so finely that the question becomes impossible to ask in practice. The puzzle is not solved. It is hidden, exquisitely, exactly where we left it. And the quantum world has one more habit that ought to be impossible, and yet underwrites your existence every second. In the ordinary way of thinking, if a ball does not have enough energy to roll over a hill, it stays on its side of the hill. Full stop. A barrier is a barrier. But a quantum particle facing a barrier it has no right to cross can sometimes simply appear on the other side, as though it had slipped through a wall without ever climbing over it. This is not a trick of insufficient measurement. It is a real and constant feature of how the smallest things behave. A leaking of possibility through obstacles that classical intuition says are sealed. And far from being a laboratory curiosity, it is the reason the stars shine. In the core of a star, atomic nuclei that should repel one another fiercely, that by the older rules could never get close enough to fuse, nonetheless manage to merge, because every so often they tunnel through the barrier between them, passing where they should not be able to pass. The light that warms every world, the energy that has driven the slow construction of the elements over cosmic time, depends on particles routinely doing something the everyday picture of reality forbids. The world we call solid and lawful is built, at its base, on events that look like quiet impossibilities, repeated beyond counting. The rules are not the rules we would have guessed, and the fact that we are here at all rests on their strangeness. If reality refuses to settle into a single definite state until it is interacted with, then the stage on which all of this unfolds deserves a closer look. Because time itself, the steady flow we feel carrying us from one moment to the next, may be the deepest illusion of all. When physicists tried to apply the quantum description, not to a single particle, but to the entire universe at once, treating the whole of everything as one vast quantum system, They wrote down an equation meant to capture its complete state. And the equation that emerged had a startling feature. It contained no time. Not a hidden time variable waiting to be teased out. Not a quantity disguised by a clever choice of coordinates. Simply no time at all. The parameter that appears in every other equation in physics, the independent flow against which all change is measured, was missing entirely from the fundamental description of the universe as a whole. It is tempting to treat this as a technical accident, a sign that the equation is unfinished and will someday be corrected. That is a reasonable position. It is also a position that has been held for half a century, while the time variable stubbornly refuses to appear. At some point, the absence itself becomes the message. It arises from the way the theory of gravity treats time not as an outside clock ticking independently, but as part of the very geometry of the universe. So that when you try to fold gravity into the quantum picture, time gets absorbed into the system rather than standing behind it. What you are left with is an equation that seems to describe every possible configuration of the universe all at once, with no preferred order, no before, no after. Picture a single photograph of a face. The photograph does not move. It holds every detail of one moment frozen into a still image. This description of the universe is like that photograph, except it appears to hold every configuration the cosmos has ever taken, or ever will take, all present together, with the sequence we experience as time nowhere written into the underlying picture. That idea finds a strange echo in one of the most firmly established results in all of physics, a consequence of the discovery that the speed of light is the same for every observer no matter how they move. From that single fact follows something the human mind has never fully digested. There is no universal now. There is no single instant that counts as the present for the entire universe at once. Two observers moving differently will disagree about whether two distant events happened at the same time, and there is no fact of the matter that settles which of them is right. Simultaneity is not a property of events themselves. It depends on the motion of whoever is asking. And if which events count as simultaneous depends on the observer, then the clean division of time into a fixed past, a fleeting present, and an open future also depends on the observer. The only thing every observer can agree on is a four-dimensional whole in which space and time are woven together, and in that whole, no single slice is privileged as the present moment. This is the picture sometimes called the block, in which all moments of time exist with equal reality, the way all places in space exist whether or not you happen to be standing in them. Your earliest memory and your final breath are, in this view, both simply there, fixed points in the four-dimensional geometry, no less real than the instant you are living right now, the overwhelming sense that time flows, that the present is sliding forward, and the past is gone, and the future is rushing toward us, would then not be a feature of the universe at all, but a feature of how awareness moves through a structure that does not itself move. Think of every page of a book existing all at once between its covers. The characters live their story in sequence, but the sequence is in the reading, not in the paper. The pages do not turn themselves. On this view, what we call the passing of time is the reading, not the book. A story told page by page, through a structure where all the pages already exist. But if all moments are equally real, a glaring puzzle appears. Why does time so obviously run in one direction? Why do we remember yesterday and not tomorrow? Why does a shattered cup never gather itself back together? Why does heat always drain from the warm thing into the cold one, and never the reverse? At the level of the fundamental laws, almost nothing distinguishes forward from backward. Take the equations describing a basic physical process and run them in reverse, And the reversed process is just as allowed, just as physical. A film of two balls colliding looks perfectly sensible played either way. So the arrow we feel so strongly is not stamped into the basic laws. It comes from something subtler, from counting. A shattered cup can be arranged in vastly more ways than an intact one. There is only a narrow set of arrangements we would call a whole cup, and an astronomical number we would call a broken one. Disorder is not preferred by any law. It simply has overwhelmingly more ways to happen. Scramble a system at random, and it almost certainly lands in one of the countless disordered states, rather than one of the rare ordered ones. That is the origin of time's direction. The reason the past feels fixed and the future feels open is not written into the deep machinery of physics. It traces back to the way the universe began, in an extraordinarily ordered, smooth, improbably tidy state, and to the long slide toward disorder that has been unfolding ever since. Imagine someone who spends hours arranging grains of sand into an intricate pattern, and then a single gust scatters it. The gust did not violate some law against beauty. It merely introduced random motion. And random motion overwhelmingly favors the countless messy arrangements over the few orderly ones. The pattern was the rare exception. The mess is the default. Our universe began as the pattern, and it has been drifting toward the mess for nearly 14 billion years, and that drift is the arrow we feel. Why the beginning was so exquisitely ordered in the first place is a question the counting cannot answer. Time points the way it does, because we started somewhere extraordinarily special. And where that special starting point came from is a question that sits beneath everything else and refuses to go away. There may even be a smallest possible tick of time, a shortest interval below which the very notion of duration loses its footing, a grain of time as fundamental as the grain of space, fantastically brief, far shorter than anything any clock could ever resolve. Below that scale, our equations stop producing sensible answers, and some have argued that time there is not a smooth flow at all, but a discrete succession of quantum steps, with no time in between them. Not slow time, not frozen time, but no time whatsoever. Think of a film built from still frames flashed in rapid succession. Between the frames, the screen is dark, and the motion you perceive exists only in the frames themselves. If the projector ran slowly enough, you would begin to see the gaps, and the smooth illusion would break into the still images it was always made of. Reality, at the very bottom, may be assembled frame by frame at a rate beyond comprehension, with the continuity we experience stitched together from a flicker of discrete instants. And what does the stitching, what carries the universe from one frame to the next, is exactly the kind of question that sits underneath all the others, waiting. If space may be a network of relationships, and time may be a flicker of discrete frames, then it is fair to ask what the universe is truly made of, beneath the particles, and the fields, and the forces. And a growing line of thought gives an answer that would have sounded absurd a century ago. The answer is information. One of the great physicists of the last century spent decades circling this idea before stating it plainly, that every physical quantity, at the deepest level, comes down to the answer to a yes or no question. A particle is detected, or it is not. A measured property comes out one way, or the other. At the level of fundamental interaction, the universe seems to speak in nothing but these binary answers, and the suggestion is that the information is not a description laid over the matter, but is somehow more basic than the matter itself. That a particle is what you get when the universe answers a question. That matter is crystallized information. That the geometry of space is the geometry of how that information is related. Think of a conversation between two people. The conversation is not made of the air that carries the sound. It is made of meaning. On this view, the universe is more like a conversation than like a machine. And the message is what is real. This is not idle poetry. It connects to one of the most surprising results in the study of the dark hearts where stars collapse. When physicists worked out how much disorder such an object can contain, how much information it hides, they found that the amount does not scale with its volume, as you would expect for something filling a region of space, but with the area of its boundary, the surface enclosing it. The information lives on the surface, not in the interior. Pushed further, this becomes a startling general claim that everything happening inside any region of space can be completely captured by information written on the two-dimensional boundary around it, with a fixed amount of information for each tiny patch of that surface. Imagine one of those glass spheres with a scene sealed inside. Everything within it looks fully three-dimensional. Yet if this principle holds, all of that interior could be encoded on the surface of the glass. The depth, a kind of projection of information stored on the boundary. The space you move through, with all its apparent volume, may be a reading out of a structure that is fundamentally one dimension flatter. Not a trick or an illusion in any cheap sense, but a deep statement about where the information that makes up the world is actually kept. And information, it turns out, is not free. It carries a physical cost that no cleverness can ever escape. Decades ago, a researcher proved that the act of erasing a single piece of information, resetting a two-state system to a known condition, cannot be done without releasing a minimum amount of heat into the surroundings. A floor set by the laws of thermodynamics that no future technology can ever dig beneath. Erasing is irreversible, and reducing the number of possibilities a system could be in always exacts a thermal price. The startling implication is that processing information is a physical act with a physical cost. That even a perfect, lossless computer would still shed heat the moment it erased anything. Think of thought as the burning of fuel. Every time a piece of information is wiped and rewritten, a little warmth escapes. Not from any flaw in the design, but from the structure of physics itself. And the universe has been processing information since its first instant. Every interaction between particles is, in a sense, a tiny computation, paying the thermal toll of its own operation. And it has been doing so without pause since the very beginning. If this is right, then information is not merely our way of talking about reality. It is closer to what reality is. And the cosmos has been quietly spending itself to compute its own unfolding from the start. The most disturbing connection of all came when physicists noticed that two ideas that had seemed entirely unrelated were, in the mathematics, the very same thing. On one side stood the strange bridges that the equations of gravity allow, tunnels that could in principle connect two distant regions of space. On the other side stood the ghostly link between particles that have interacted and then separated. A correlation so deep that measuring one seems instantly tied to the state of the other, no matter how far apart they have drifted. These looked like utterly different phenomena, one belonging to the grand geometry of space, the other to the quantum behavior of particles. And yet the suggestion that emerged is that they are two faces of a single thing, that the connection between entangled particles is itself a kind of microscopic bridge, and that the smooth fabric of space is woven, thread by thread, out of these quantum links. Picture a net made of countless knots tied together by string. Cut all the string, and the knots do not drift apart into a larger net. They stop being a net at all. Space may be that net, and entanglement the string that holds it together. On this view, space is not the empty container in which events happen. Space is a consequence of the web of relationships among quantum systems. And if you could sever those relationships, The space between things would not grow vast. It would simply cease to be. Reality holds its shape not because space is a solid stage, but because the connections are intact, and the structure we trust is less a fixed fact than an ongoing weave. These threads all pull toward the same vertiginous question, the one about origins, and here the deepest cosmology becomes a parade of brilliant guesses, each one running into the same wall. Some have proposed that the universe had no sharp beginning at all, that if you trace time back toward the first instant, the dimension of time gradually loses its distinctness and behaves more like a dimension of space, so that asking what came before the beginning is like asking what lies south of the southernmost point on a globe. The question sounds reasonable, but has no answer because the direction simply runs out. There is no further south to go, and in this picture there is no further back to go either. The universe is finite in its past without having an edge, the way the surface of a sphere is finite without having a boundary. Others have proposed that the Great Expansion was not a beginning but a transition, a violent handoff of energy that looked from inside like the birth of everything, yet was preceded by an earlier state and will be followed by later ones. Our universe, one episode in a far longer cycle of expansion and renewal. Still others have suggested that the cold, dark, empty end state toward which the cosmos is sliding, the featureless expanse where no process can occur, shares a deep mathematical likeness with the hot, dense conditions of a beginning, so that the far future of one universe could, in the right mathematical sense, be stitched to the dawn of the next, with maximum emptiness and fresh beginning turning out to be two descriptions of the same geometry. Each of these pictures is ingenious. Each of them dissolves one version of the origin question, and every single one of them, without exception, has to assume something it cannot derive. Each must take certain conditions as simply given, a particular state of energy, a particular degree of order, a particular geometry to start from, and write them in by hand without explaining why those conditions, and not others. Think of a calculator that faithfully produces a result the moment you enter a number, but can never tell you where the number came from or who typed it in. The universe, in every one of these accounts, is the calculator, and the starting conditions are the number entered at the outset, and no theory in the set can say whose hand pressed the keys. Any explanation must begin somewhere, must rest on some assumption taken as a given. And a theory that derives its starting assumptions from still deeper assumptions has not closed the gap. It has only moved it down a level. The chain of because does not bottom out in something self-evident. It bottoms out in a foundation that has to be granted, rather than proven. And that is not a temporary shortcoming of today's physics. It appears to be the very shape of explanation itself. There is a line of thought that tries to leap over this wall entirely, and it begins with a simple observation about mathematics. The patterns of mathematics do not seem to depend on us. A particular relationship among numbers holds whether or not anyone has ever written it down. The same truths that a thinker could establish thousands of years ago hold in a laboratory today, unchanged, and they would hold in any other corner of the cosmos as well. The primes fall where they fall. The relationships that govern circles and triangles and the curve of a falling stone do not bend to opinion or era. This durability has led some to a radical suggestion that the deepest description of reality is not a set of words or pictures, but a mathematical structure, and that if such structures have a kind of existence independent of whether anyone writes them out, then perhaps the description does not merely represent the universe, but is the universe. That we are not beings described by a structure, but, in some sense, patterns within one. On this view, the question of why this particular reality exists begins to look less like why was this built, and more like why would this pattern fail to be, with existence as the expected state, and absence as the thing that would need explaining. It is a dizzying idea, offered seriously, and it cannot at present be tested, which leaves it suspended in the same uncertain air as so much else at this depth, possibly a profound insight into the nature of things, possibly a question dressed up as an answer. A close cousin of this idea looks not at structure, but at process. If reality follows rules at all, and if those rules are simple enough at bottom, then everything we see, the swirl of galaxies, the branching of a river, the firing of thoughts in a mind, could in principle arise from the patient repetition of a few elementary steps, applied over and over across the smallest grains of space and the smallest ticks of time. It has been shown that astonishingly simple rules, repeated, can generate complexity without limit, patterns rich enough to carry out any computation that can be described at all. From this comes the conjecture that the universe itself might be something like the unfolding of such a rule, with space and time and matter not fed in as ingredients, but produced as results, output by a process running step after step. And if reality could be the output of a rule, then the question of where the rule came from, and why these rules rather than some others, comes rushing back, sharper than before. Every attempt to reach the bottom turns out to be a trapdoor, opening onto another room. There is one more thread, and it is the one that loops back to touch us directly. Across several of the strangest results, the way a particle seems to remain a blur of possibilities until it is observed, the way the delayed choice experiment seems to let a present decision settle a past event, the way some accounts treat the quantum description as a ledger of an observer's knowledge, rather than a portrait of the world. There runs a common, unsettling suggestion. It is that the crisp, definite, located reality we take for granted may not be the natural resting state of the universe at all, but something that becomes definite only through the act of interaction and observation. Strip away every observer, every device, every system capable of registering anything about anything else, and what the equations seem to describe is not a tidy world quietly carrying on, but a vast, unresolved blend of every possibility, with nothing singled out, nothing pinned down, not nothing at all, but nothing definite. One serious interpretation holds that physics does not describe a world standing apart from observers. It describes the relationships between observers and what they encounter, with the map and the territory tangled together in a way that resists being pulled apart. This must be handled with great care, because it is contested ground, and reasonable physicists disagree sharply about what it means. But even in its most cautious form, the idea is humbling. It suggests that the sharpness and solidity of the world, the very definiteness that makes a stone and a moment, might be less a fixed property of the universe, and more a feature of how the universe and its observers meet. Think of a standing wave that forms in a flowing stream, a shape that seems to hold steady, with a definite crest and a definite place, yet exists only because the water keeps moving through it. Stop the flow and the wave does not move elsewhere. It simply ceases to be a wave. Some have wondered whether the definite reality we know is more like that wave than like a stone, a pattern sustained by an ongoing process rather than a thing sitting inert on its own. Whether or not that turns out to be the right way to see it, the mere fact that the most precisely tested theory in science can be read this way, and that no experiment has yet ruled it out, tells you how far the solid ground of common sense has receded once you press toward the foundations. And so the chain of questions arrives, Finally, at the oldest and simplest of them all, the one a thinker posed centuries ago in a single sentence that has not been answered in all the years since. Why is there something rather than nothing? Not how did the something begin, not what rules does it obey, but why is there existence at all, rather than a perfect and total absence? Notice that every physical theory ever written quietly assumes its way past this. One assumes fields, another assumes space and time, another assumes vibrating threads. Each begins by granting that there is something for the laws to act upon. None of them explains why there is anything to be governed in the first place. This is not a gap at the edge of physics, out near the frontier of what we have not yet measured. It is a gap beneath physics, underneath the deepest layer any equation reaches, in the place where the foundation should be, and where, instead, there is only the bare and astonishing fact of existence itself, sitting there without a because. This is the wall, not the edge of today's knowledge, which sharper instruments and cleverer theories will surely push outward, but a genuine boundary where the tools of explanation themselves run out, not because they are dull, but because sharpening them does not help. Every answer that physics offers turns out to assume something deeper, and every attempt to explain that deeper thing assumes something deeper still, and the regress does not terminate in some self-evident bedrock that needs no support. It is the honest situation of a mind trying to account for the very reality it is part of, from a vantage point that can never step outside the whole to see it entire. And it is worth being clear about what this is and is not. It is not a failure of science. Science has been spectacularly, almost miraculously successful at describing how the world behaves, at predicting and building and revealing. And none of the strangeness explored here diminishes that. What the journey reveals instead is the boundary of a particular kind of question. The difference between describing the workings of reality, which physics does superbly, and explaining why there is a reality to work at all, which lies on the far side of a line that measurement cannot cross. To feel how sharp that line really is, it helps to stand at the one place in the cosmos where both of our great descriptions are forced to speak at once, and where they shout past each other in mutual contradiction. That place is the collapsed remnant of a massive star, the region where gravity has grown so overwhelming that it crushes matter past every limit and wraps space around itself so tightly that not even light can climb back out. From the outside, such an object is defined by a surface of no return, a boundary that is not a wall of any material but simply the place beyond which every possible path leads inward. Cross it, and there is no trajectory, however fast, that points back toward the stars. The theory of gravity describes this beautifully, predicts these objects cleanly, and we have now seen their silhouettes directly, and heard the ripples they send through space when they collide. But gravity alone says that at the very center lies a point where its own equations break, where density and curvature climb toward the meaningless infinities that signal a theory pushed past its domain. To know what truly happens there, you would need the quantum description to step in. And when it does, the two refuse to agree. The clash sharpens into outright paradox over a question that sounds almost childish. What happens to information that falls into such an object? Quantum theory holds, as one of its most cherished principles, that information is never truly destroyed, that in principle the complete history of any system is preserved, however scrambled, never erased from the universe. Yet these collapsed objects are not entirely black. They slowly leak energy, a faint glow arising from the restless quantum activity at their very edge. And over unimaginable spans of time that leak causes them to shrink, and, eventually, to vanish altogether. The trouble is that the escaping glow appears to carry no detailed memory of whatever fell in. Drop a library, a star, a lifetime of records past the boundary. Wait out the eons until the object evaporates entirely. And the radiation left behind seems featureless, the same regardless of what was swallowed. The information should be indestructible, and yet it appears to be gone. Two pillars of physics, each tested to extraordinary precision, point to opposite conclusions about the same event, and resolving the contradiction has consumed some of the finest minds for decades, spawning ideas stranger than the puzzle itself, that the information is somehow smeared across the boundary surface, that it leaks out encoded in subtle correlations too faint to notice, that the inside and the boundary are in some sense the same information described two ways. No one knows which, if any, is correct. The place where reality is most extreme is exactly the place where our knowledge is most divided against itself. And the strangeness is not confined to such violent extremes. It hides in the gentlest of setups, in the quiet correlation between two particles that once touched and then went their separate ways. Prepare a pair of particles together in the right manner, and they become linked in a way that has no everyday counterpart. Measure a certain property of one, and the corresponding property of the other is instantly fixed, no matter how far apart they have traveled. Across a room, across a planet, in principle across the galaxy. For a long time, the natural assumption was that the particles simply carried hidden instructions all along, settled at the moment they parted, like two travelers each handed a sealed envelope, whose contents were merely revealed, not decided, when opened. But careful reasoning showed that this comforting picture makes predictions that differ, in measurable ways, from what quantum theory predicts. The experiment was done, again and again, with ever tighter controls closing off every loophole. And the verdict has been consistent and stark. The comforting picture is wrong. The particles do not carry pre-written answers. The correlation between them is deeper and stranger than any hidden script could produce. A connection that does not fit our intuitions about separate objects in separate places, carrying their own private properties. This does not mean signals race between them faster than light. You cannot use the link to send a message, because each measurement on its own looks completely random. And only by comparing notes afterward do the correlations reveal themselves. But it does mean that two particles can behave as a single, indivisible whole, even when a great gulf of space lies between them, as though distance were not the absolute separator we imagine. And it is precisely this kind of connection that some now suspect is the very thread from which space is sewn. The deeper you look, the less the world resembles a collection of separate things sitting at separate places, and the more it resembles a single fabric of relationships, with the apparent separateness of objects a feature that emerges at our scale, rather than a truth that runs all the way down. There is one more place where the universe quietly hands us a riddle, and it is the oldest light there is. Look far enough out into space and, because light takes time to cross such distances, you are looking far enough back in time to see the cosmos as it was when it first turned transparent, long before stars, when everything was a smooth, hot glow. That ancient light still bathes the whole sky, stretched now into a faint hum of radiation coming from every direction, and when we measure it, we find it is almost perfectly the same temperature everywhere we look, to a precision that ought to be impossible. Regions on opposite sides of the sky, so far apart that in the ordinary history of the universe they could never have exchanged any influence, never shared heat, never come into contact in any way, nonetheless match one another to extraordinary accuracy, as though they had somehow agreed on a common temperature before they were ever able to communicate. It is as if you found two distant lakes with no river between them and no shared source, sitting at exactly the same level to the millimeter, and had to explain the coincidence. The leading attempt to account for this is that sudden, violent stretching of the early universe, which would have taken a single tiny patch that had reached a common temperature and blown it up to enormous size, planting that uniformity across the whole sky. It is an elegant idea, and it explains a great deal. But it leans on conditions of its own that have to be assumed, and it opens the door to the endless budding of universes we met before. Even the smoothness of the sky, when you stare at it long enough, turns into another question that points downward toward the foundation. There is also a hard limit on how much of all this we will ever be allowed to examine, and it is built into the geometry of an expanding universe. Because space has been stretching since the beginning, and because light travels at a fixed speed, there is a maximum distance from which any signal could have reached us in all the time the universe has existed. Everything inside that distance we can, in principle, observe. Everything beyond it is sealed away. Its light still in transit or, in the farthest reaches, never able to arrive at all. Because the space in between is stretching faster than the light can close the gap, we live, in other words, inside a finite bubble of the visible, with an unknowable amount of cosmos lying forever past its edge. And as the expansion accelerates, that edge is slowly drawing inward in a sense. Distant galaxies are being carried beyond our reach, their light redshifting toward invisibility, so that the observable universe of the far future will be lonelier and emptier than the one we see now. Whatever lies past the horizon, whether space goes on similar to ours, or changes character, or simply continues without end, is a question no instrument will ever settle. Not because we lack the cleverness, but because the information is physically prohibited from ever reaching us. We are studying reality through a window of fixed size, and we have no way to know how much of the house lies in the rooms we can never enter. So consider, for a moment, the full sweep of what the careful study of reality has turned up, not as a list of disconnected curiosities, but as a single accumulating weight. The ground state of space may not be the true bottom, but a perch above a deeper drop. The energy of empty space is wrong, by the most extreme margin in the history of measurement, in a way that should have prevented anything from forming. And yet here everything is. The constants that permit stars and chemistry and time sit in vanishingly narrow bands, with no known reason. The attempts to explain those constants reach either for an unprovable ocean of other universes, or for a deeper theory that keeps receding. The most ordinary motion follows a path of perfect economy, for reasons no one can state. Space may be a discrete web rather than a smooth sheet, and that web may rest on nothing. Our two finest theories cannot be spoken in the same breath at the places that matter most. Logic itself hints that a complete account from the inside may be unreachable. The quantum world will not say what it is. Time may not flow. The past may not be fixed until it is read. And the very definiteness of things may depend on their being met by something that observes them. And underneath all of it sits the plain, unanswerable astonishment that there is anything here at all. It would be easy to take all of this as a counsel of despair, as if the lesson were that we know nothing and can know nothing. But that is not the lesson, and reading it that way would miss something extraordinary hiding in plain sight. Pause and consider what is actually happening when a mind follows this trail of questions. A small arrangement of matter on the surface of one ordinary world, orbiting one unremarkable star among an unfathomable multitude, has managed to weigh the energy of empty space, to clock the expansion of the entire cosmos, to predict the inner structure of an atomic nucleus from the bare fact of its own existence, to detect ripples in space a fraction of the width of a proton, to image the shadow of an object from which light cannot escape, and to trace the history of everything back to the first transparent glow. The same strangeness that humbles us is strangeness we discovered. The walls we keep running into are walls we found by walking toward them, deliberately, with instruments we built and mathematics we invented, pushing into the dark on purpose. There is something almost vertiginous in that. A portion of the universe has woken up enough to ask what the universe is, and to be genuinely unsettled by the answers. And the scale against which that small waking mind is working is worth holding steady for a moment, because it sharpens everything. The world you stand on is a speck circling a fire that is itself one of hundreds of billions of fires bound together in a single slow-turning island of light. And that island is one among a number of others so large that no one will ever count them. Between those islands lie gulfs so wide that the light crossing them set out before there were eyes anywhere to receive it. Reach down instead of out. And the smallness is just as dizzying. The matter you are made of is, when you look closely enough, almost entirely empty. Vast spaces between specks. The apparent solidity of your own hand, a kind of agreement among forces, rather than a filled-in fact. You are suspended between the unimaginably large and the unimaginably small, built from the same handful of ingredients as the stars. And somehow this in-between thing that you are can hold both ends of that range inside a single thought, that a structure so modest can model a cosmos so immense is, when you sit with it, stranger than any single discovery along the way. It is worth remembering, too, where we sit in the long story of time, because that placement is its own quiet marvel. The universe was not always able to be understood, and it will not always be legible either. In its earliest moments it was too hot, and too dense, and too violent for anything like a thinking thing to exist, let alone to look around. And in its far future, across spans of time that make the present age seem like the first breath of a long life, the stars will burn out one by one. New ones will cease to form, as the raw material runs thin, and the accelerating expansion will carry the distant galaxies past the horizon until the sky empties of almost everything that once filled it. A mind awakening in that remote era would look up and see very little. No swarm of galaxies stretching to the edge of sight. No clear record of the beginning written in ancient light. Only its own dimming island, adrift in a darkness that gives almost nothing away. The clues that let us reconstruct where everything came from are not permanent fixtures. They are features of this particular chapter, and they are slowly slipping out of reach. We happen to be alive in a window when the universe is still bright enough to read, still young enough to remember its origins, still generous enough to leave the evidence lying within view. That window will not stay open forever. Of all the eras in which a mind could have arrived to ask these questions, this is one of the few from which the answers are even partly visible, which makes the asking, right now, not only remarkable, but rare. A privilege of timing as much as of intellect. There is a particular kind of courage in continuing to ask anyway. Every generation of those who study these questions inherits a map with a blank seam running through its center, and instead of looking away, they walk straight toward the seam, knowing they will likely hand it on still unfinished to whoever comes after. The person who reasoned out the hidden property of carbon from the simple fact of being alive did not have the tools to be certain. They had a conviction that the universe was the kind of thing that would answer if asked precisely enough. And they asked, and it answered. That is the temper of the whole enterprise. Not the arrogance of believing the final answer is near, but the stubborn, almost reckless faith that the questions are worth asking even when the floor keeps dropping away beneath each answer. The regress that has no bottom is not only a frustration, it is also an invitation that never closes. A horizon that recedes precisely because every step forward is real. So what should you do with the discovery that the ground beneath everything is not the bedrock it pretends to be? Perhaps the honest response is neither dread nor dismissal, but a kind of widened attention. The cup on the table, the light through the window, the weight of your own body in the chair. These are not less real for resting on a foundation we cannot fully see to the bottom of. If anything, they become more astonishing, because their steadiness is not the dull steadiness of something that simply had to be, but the quiet, improbable steadiness of something holding its shape against a backdrop of staggering strangeness. Every ordinary moment that passes without the floor giving way is, viewed from this depth, a small marvel rather than a guarantee. The solidity you feel is genuine within the only world you will ever inhabit, and it is also, at the same time, a provisional arrangement balanced on questions that reach far past the edge of what can be measured. Both of those things are true at once, and learning to hold them together is its own kind of understanding. The deepest questions, the ones beneath all the others, may simply not be the kind that measurement can ever reach. Why there is something rather than nothing? Why these rules and not others? What holds the arrangement in place when the equations themselves cannot say? These sit on the far side of a line that no telescope will cross, and no collider will breach, because they are not questions about how the world behaves, but about why there is a world to behave at all. Science can carry us right up to that line, can show us with breathtaking precision exactly where it lies, and how strange the territory becomes as we approach it. And that itself is a gift beyond reckoning. But it cannot carry us across, and there is a kind of peace available in seeing that clearly, in knowing the difference between the questions we can answer and the ones we can only stand before. The wonder does not run out when the explanations do. If anything, that is where it begins. So the next time the world feels heavy and ordinary and entirely too solid, remember what is actually underneath it. Remember that the emptiness you cannot see fizzes with an energy our finest theory cannot account for. Remember that the constants holding your atoms together sit in a band so narrow it has no name. Remember that the smooth space you move through may be a web of relationships stitched from connections finer than anything you could ever touch, and that the steady tick of time may be a flicker assembled, frame by frame, from instants with darkness in between. Remember that a part of all this immensity managed to look back at the whole and ask why, and that the asking, even without an answer, is among the most remarkable things the universe has ever produced. The reality you trust did not have to be simple, and it is not. It is far stranger than it looks, far less finished than it feels, and far more astonishing than any story we could have invented to replace it. And you are not merely watching it from a safe distance. You are made of it, threaded into it. A small bright knot in the great fabric, awake, for a while, inside a mystery that has no bottom and no edge, and able, for as long as the looking lasts, to be amazed.